Assalamu alaikum and a very good morning to all the panels and the presenters. My name is Muhammad Hilmi Naim bin Muhammad Yakin. I am a PhD student from University Malaysia Pahang, UMP. My topic for the presentation today is a quasi-brittle damage model in the framework of bond-based peridynamics with adaptive dynamic relaxation method. So before I explain about what is peridynamics, let me give a little brief about the most famous computational technique that we call finite element. So finite element method, or in the short form we call it FEM, is the most widely used method that we use to solve problems involving engineering and mathematical model, such as structural analysis or traditional stress analysis. But since this method are based on the partial differential equation, or we call PDE, the spatial derivatives that is required by PDE do not exist at crack tips or along crack surfaces. So easily being said, this mathematical structure or formulation will break down when a crack appears in a body. So this is where peridynamics methods comes. So peridynamics is a new tool for modeling fracture mechanics, where a domain is represented by particles connected through the physical interaction. Peridynamics theory, they use spatial integral equation, where this integral equation can be applied to discontinuity. So the figure on the right, on my right side of the slide, shows that every point in the material denotes the location of a material particle in body that is represented by the symbol beta, and these infinitely many material points, or we call particles, constitute the continuum. An infinite number of interactions may exist between the material point at location X and other material points. However, the influence of the material points interacting with X is assumed to vanish beyond something that we call horizon. In this area, in this figure here, we denoted it by HX, capital HX. So this is why people or researchers are getting interested into the study of failure prediction in quasi-brittle materials, because this kind of problem still remains an open and a major challenge for researchers, in particular for cases that contain complex fracture phenomena such as spontaneous crack nucleation. So peridynamics enables predicting the complex fracture phenomena such as spontaneous crack or crack branching, curving, and arrest. So this research focuses on the implementation of a novel quasi-brittle damage model, QBR model, with adaptive dynamic relaxation method for quasi-brittle material in the framework of bond-based peridynamic. Okay, now this slide shows the differences between first one local continuum model and the second one non-local continuum model. Peridynamics is one of the non-local continuum model, and another one is molecular dynamics. So, in the case of the local continuum model, the state of a material point is influenced by the material points that is just located in its immediate vicinity only, as in the first figure on our left-hand side. Now, in the case of the non-local continuum model, the state of the material point is influenced by material point that is located within a region of finite radius, as in peridynamics. This is to note that as the radius becomes infinitely large, the non-local theory becomes the continuous version, or we call it molecular dynamics model. Okay, in peridynamics, there are three kinds of peridynamics, where the first one is bond-based peridynamics, or in the short form we call it BBPD. The second one is ordinary state-based peridynamic, or we call it OSB-PD. And the third one is non-ordinary state-based peridynamic, or NOSB-PD. What are the differences between these three kinds of peridynamics? Okay, let me go for the first one first, that is bond-based peridynamics. So bond-based peridynamics theory is a peridynamic concept that is concerned with a pairwise interactions of material points. So if you can see from the figure on the left, the forces between two material points is on the same direction and also same magnitude. Now we move to, as shown in the middle figure, the force density vectors for ordinary state-based, the force density vectors having unequal magnitudes, while it is being parallel to the relative position vector in the deformed state. And in the last one, for non-ordinary state-based, the deformation of material points developing unequal force densities and also in arbitrary direction. So if you can see from the figure, you can have a clear view of what are the differences between these three kinds of peridynamics. So this is the flow chart of the study. So the first one is we need to find the literature, and then we will I will need to write the algorithm for QBR damage model in the framework of bond-based peridynamics with adaptive dynamic relaxation. After that, the coding will be written and debugged by using MATLAB software, and then the MATLAB code will then be verified using simple problems to make sure that there is nothing problem with the code. And in case if there is any problem with the code, and then it will be updated before it is being run on a numerical problem, and then to provide the results. So here, this is the main equation in peridynamic, the equation of momentum, the integral function of a force on particle at x to replace the divergence of the stress term. So this is the main equation of bond-based peridynamics, where the one on the left-hand side is the total momentum, and the one on the right-hand side of the equation is the summation of all the forces in the material points. So the summation here it means the summation of all the forces in the material points. Now this slide shows the difference between the PMB damage model, or we call it prototype microelastic brittle damage model, and also QBR damage model, that is quasi-brittle damage model. So if you can see that on the left graph shows that the bond force increases linearly with the bond stretch, or S, and drops abruptly to zero when the bond stretch reaches its critical value, or S naught. But on the right hand side, in QBR damage model, the bond force did not drop abruptly to zero. Instead, it will going down the curve exponentially until the value of the force reaches zero. So this is the numerical example that we analyze, a problem of an isotropic plate with a hole at the center under quasi-static loading along its horizontal edges. The material properties for this isotropic plate is as stated: the Young's modulus of 192 gigapascal, Poisson's ratio of 1/3, and the mass density of 8,000 kilogram per meter cube. And the geometric properties of this isotropic plate are the length and the width are the same, 50 mm, and the thickness is 50 mm as well, and the diameter of the hole at the middle of the plate is 10 mm, and this plate we applied the velocity along its horizontal edges at the top and at the bottom for 2.7541 times to the power of -7 meter per second. So the figure shows the variation of horizontal displacement on the left side and vertical displacement on the right side along the central axis at the end of 1000 time steps when failure is not allowed. So in this figure, it shows a very good agreement with the result from FEM analysis. Now this slide shows the plot of the damage plot of the specimen between PMB damage model and QBR damage model when the failure is allowed to happen at time step of 700, 800, 900 and 1000. So as a conclusion, it is found that the damage model with ADR and the quasi-static loading significantly improves the prediction of failure process by taking into account the progressive degradation of peridynamics bond stiffness. And it is also shown that this damage model managed to model a more realistic damage model with respect to the PMB damage model. This model, therefore, opens the door for peridynamics to be used for a wider class of material in the prediction of failure in the future. I would like to thank my supervisors. The first one to Professor Dr. Nikabdullah bin Muhammad. The second one, Professor Dr. Muhammad Ruzaini bin Rejab. And the last one is Dr. Olaf Wegner, who has inspired me a lot throughout my research by always having a really useful discussion that enhance my knowledge and understanding and interest towards peridynamics. Thank you very much.